So, welcome to this particular lecture. So, in the previous lecture we showed the insights, right, that what happens when you use the extended model, what is the difference between the extended model and the effective conductivity model, and how it can predict the temperature and all those other things, okay, and how what would the isotherms actually look like, what is the transition between a conduction to a convection and convection to conduction during the lifespan of a single droplet. So, it is heavily dependent on the life history of the droplet. Is not just a conduction or a convection dominated problem, it is actually a mixture. So, let us look at the solution process that was suggested by Abramson and Scirinniano. So, Professor Scirinniano, he is basically the pioneer in the work in anything related to droplet evaporation, combustion and things like that, both from the modeling as well as the experimental perspective. Now, the extended model, if we look at the extended model, how is it solved? How is the extended model actually solved? Okay. So, we gave you the idea that what is a gas phase, what is a liquid phase and what are the outcomes, but let us just give you an idea how this whole thing is solved. Okay. So, the first step that people do is calculate, and this is solved numerically. So, I am just giving the algorithmic step, okay, right, what you do from the gas phase perspective. Calculate the molar and the mass fraction of fuel vapor. Okay. So, like XFS is like PFS by P, YFS, that is the mole fraction, this is the XFS into the molecular weight divided by summation of Xi Wi, right. So, PFS is basically a function of the surface temperature. This is basically the saturated vapor pressure calculated from the Clausius-Clapeyron equation, right, using Clausius-Clapeyron. So, from a numerical point of view, these are the steps that one can follow. Clapeyron equation. Step 2, calculate the average properties. Average properties here means rho bar, CPF bar, kg bar, mu g bar, etc. in gas film. Up to this step it should be fairly easy, right. This is how you actually normally calculate, right. So, you are using the Clausius-Clapeyron equation to calculate the mass fraction and the mole fraction, okay, on the gas side, okay, and then you are using the average properties in the gas film, okay. Then the third step is that you basically calculate RE. This is the gas phase Reynolds number, as we know. If you recall, that was what, U minus U infinity Rs divided by mu g, right. You also calculate Nu naught and Sh naught. We have defined all these quantities earlier. These are all related to your Reynolds number, that also we showed, right. So, you can calculate all these quantities in step 3, right. So, let us go and look at in step 4 what do you do. In step 4 you calculate Bm, Fm, Sh star and m dot, all from the mass point of view, okay, all from the mass point of view. You are calculating all the quantities like Bm, Fm, Sh star and m dot. M dot is the mass flux, right. Then step 5 you calculate FBT, that means that correction factor with respect to BT, okay, that is the thermal boundary layer equivalent, using BT old from previous time step. You are discretizing it, right, in terms of time. So, previous time step, whatever was the BT value there, you are using this to estimate, okay, whatever is the factor, this F factor will be. Sixth step, calculate Nu star, right. Nu star is the modified Nusselt number, we covered it in the last class. You also calculate this factor, this is the film, this is the gas, is S star nu star 1 by the Lewis number, okay, and use this to calculate Bt. Bt is 1 plus m phi minus 1, right, that we already established in the last class also, that Bt is this. Okay. Now, you return to basically step 5 if Bt minus Bt old is less than a certain value of this. Okay. This is basically the accuracy, whatever accuracy that you desire. Okay. If you want like a 10% accuracy or whatever it is, you actually do it. Then 7th step is you calculate QL, which is basically nothing but m dot Cpf, if you recall, divided by Bt minus LTS, using the value of Bt that you got from the previous time step. Got it? Why we are doing this? Because remember we told you that there is a mass limited or it is heat transfer limited, right. In order to have this equilibrium always being obeyed, okay, you need to iterate over Bt, okay, so that it does not over predict. Okay. If you just use Bt as is, right, it will over predict. Okay. So, you are limited by the mass transfer, right, in most of the cases you are limited by the mass transfer. So, you have to use Bt accordingly, right. Okay. Of course, when your Lewis number is 1 and other things, of course, this particular factor does not even come into the picture, right. So, this phi will be almost like 1. Okay. So, this is the solution process basically to iterate in the gas phase and find out what will be the value of Bt, what will be the value of QL. Once you know this value of QL, now it is very easy, because you know where QL happens, where QL comes into the picture, it comes in through the boundary condition in the liquid phase analysis, right. In the liquid phase analysis, if you recall, QL was there. If you do not, let me just pick it up and see. Here, you see this. So, there is that QL. Okay. So, QL comes from this gas phase, right. Okay. So, that QL is a QL that you are going to use in here, right. So, this QL calculation involves Bt, but Bt has to be evolved in this particular way from the mass and the heat transfer limitation. Okay. So, it cannot be just worked out like that, otherwise you can just calculate Bt as is, right, but that is not the case, because you have to match it with the mass transfer. Unless you match it with the mass transfer, this value will come overly high, okay, which will be like not the correct thing to do. Got it? Okay. So, this actually tells you that what happens when you actually have the, what is the solution process. Now, let us look at the surface tension effect also. Remember, we said that the surface tension effects are negligible because of the simple reason that there is no variation of temperature across the interface, but some people do actually have included the effect of surface tension. So, what it does is that if you recall your initial classes, you will find that this is what happens, right. Gas interface is equal to mu L at the liquid side of the interface, and then there is a d sigma by dx, right. Here of course, y is basically the normal, which is a local normal, basically local normal to the interface, and it is positive, okay, in outward direction. Got it? X on the other hand is basically the local tangent, right. Okay. So, local tangent. So, this is what the equation is actually looks like. So, the incorporation of surface tension results in an augmentation of the shear stress experienced by the liquid. If this goes to the other side, okay, if you look at the script goes to the other side, then there is an augmentation of shear stress, right, shear stress in the liquid experienced by the liquid. That makes sense, na? There is an augmentation of shear stress experienced by the liquid. So, what that will do, if there is an augmentation of shear stress, the surface velocities may actually increase, right, when you have this kind of an effect into the picture. In addition, the surface tension gradient itself can actually generate the flow, like Marangoni and this kind of flows, okay, which we knew that those are the kind of flows that can exist when we first started this discussion. So, all these things can happen, okay, but normally when you inject a droplet in a gas phase flow field, okay, the temperature equilibration around the surface happens pretty fast. Okay. So, this effect, while this can be theoretically incorporated, is not something that is kind of, I mean, useful, so to say. Okay. Let us quickly look now at the free convection. So, what is a free convection? Normally, you know, the droplets are sufficiently small to neglect any buoyancy effects, right. So, the droplets, especially in combustion related applications, okay, droplets are small, right, and usually buoyancy effects are neglected, correct. In basically, where does the buoyancy effect happens? It happens in the gas film, right. This happens in the gas film or the BL, the boundary layer, right. Now, but in some cases it may not be all that negligible. So, in order to define the effect of buoyancy, we define a number which is called a Grashof number. You know what a Grashof number is? If you do not, just open up your natural convection book, okay, and you can see what a Grashof number is. So, the Grashof number is basically G R cube. I am writing it big by this, right, okay. So, its G is the gravity, okay, R cube is the whatever is the droplet size that we are dealing with, and the kinematic viscosity square. Now, if your R is of the order of 100 micron, let us say it is of the order of 100 micron at earth gravity. The Grashof number varies from 10 to the power of minus 1 to 10 to the 10. That is the extent of variation of Grashof number, right. So, this is usually negligible, right. So, for 100 micron droplet we can see the Grashof number is like 0.1 or 1 to about 10, right. So, 1 to about 10 is usually negligible for most of the cases, not very significant. However, if R is of the order of say 1000 micrometer, okay, this leads to a Grashof number variation between order 10 to the power of 2 to 10 to the power of 3. Here buoyancy is significant, no doubt about it. Here the buoyancy is significant, understood. Okay. So, the Grashof number of that high a value 100 to 1000 is actually a significant Grashof number. So, the buoyancy effect does become very significant in this particular case, right. So, it happens in the case of large droplet, these are 1 millimeter droplet, right. So, 1 millimeter droplet you can have convection effect, right, you can have significant natural convection effect. Okay. So, from a mass conservation point of view, conservation of liquid point of view, there were two guys called Potter and Riley. They actually found out that from liquid mass conservation, they showed that this is the variation when you actually have, in the case of this is not a separated flow, this is numerically calculated, numerically done, okay, not a separated flow. Okay. So, that is the variation that these guys got, okay, the variation of the R square, okay, of the droplet, basically like the reduction in area of the droplet, where R square is more like area, right, of the droplet. That is the variation that these guys found. This is numerical results. We are not going through the motions, but we are just stating the obvious. Okay. So, many people then subsequently have undertaken for mixed mode. What happens? Mixed mode, you know what mixed mode is? Mixed mode is basically natural convection plus forced convection. Okay. So, both are actually present. Okay. So, for convective heating and vaporization, it is a combination of natural convection and mixed convection, and natural convection and forced convection. So, Fernandez-Pellow is a professor in University of California at Berkeley. Okay. So, he introduced a convection ratio. There are many people who have worked, we have just picked out one example, right. So, he defined a convection ratio called phi, not to be confused with the other phi's that we did earlier, right. That phi we also compared the Sherwood number and the Nusselt number just in the previous lecture, should not be confused with that. So, this basically is like a Grashof number divided by Reynolds number square, Ts minus T infinity divided by T infinity. There is an A, parameter A over here. Okay. So, that is the expression. This is equivalent to 4 gr divided by 9 delta u square, because Reynolds number is delta u, related to delta u. This is Ts minus T infinity divided by T infinity bar. Okay. So, this is nothing but basically the Froude number. So, what he did, his convection ratio is basically like a Froude number ratio, right. It is like a Froude number, right. Gr by delta u square is by a Froude number. Okay. So, he found that when we actually use this to calculate the vaporization rate is augmented. Vaporization rate, not augmented, is multiplied by, so whatever is the vaporization rate earlier is multiplied by phi square to the power of 1 by 8. Okay. So, the m dot that they calculate 6 by pi okay. So, this is the expression that he found for the vaporization rate. Okay. So, the vaporization rate is given by m dot into all this kind of quantities, right. So, as your phi goes to 0, right, that means this goes to 0, you actually approach pure forced convection. Got it? Pure forced convection, you go down to pure forced convection. Okay. So, that was what Pellow actually found out, Fernandez-Pellow actually found out. So, in summary, you have to do a summary. Okay. The forced and the free convection, you can write forced or free convection results in significant deviation from your d square law. There is significant deviation from the d square law, right, that we have seen, right, because for the quasi steady, so quasi steady I am writing as QS, quasi steady vaporization with forced convection, what we have is that we have a linear decrease of R by 32 versus time. this profile is linear, right, that we know, this we did earlier, right. For similar quasi steady vaporization with natural convection, NC results in r to the power of 5 by 4 versus time is linear, right. In the case of d square law, we know that r square versus time is linear, right, is not that so? So, this is r to the power of 5 by 4, this is r to the power of 3 by 2, right. So, there is a significant deviation from the d square law. The way of stating all this thing is that convection in whatever form it comes is important, right, okay, and is very different from your standard d square law. If you recall what were the assumptions taken in d square law, you would find out that this d square law is the simplest, convection was the most complicated. So, during the course of this few lectures, we have gone from the d square law all the way up to the convection, and we have shown that even if you look at it very global, from a global sense, that means you forget about temperature and other things, right, isotherms and other things, your basic vaporization rate, which is related to the reduction of the droplet diameter with time, that varies with r to the power of 3 by 2, r to the power of 5 by 4 and r square, depending on which model you are actually using. So, it is a very different class of problems, that is what the emphasis is. So, most of the things you will find that d square, people just do d square law, okay, but there are limitations, there is quite a bit of a deviation. It is not like even the profiles are actually matching, functional form of the profiles. So, if you do not get a d square law just by studying the diameter of your droplets, then I mean it makes perfect sense why it should not be that, right. Okay. So, now before we finish this discussion, okay, on the droplets, okay. So, now let us imagine that the droplet has now got a non volatile entity. That means, let us say for example salt plus water. Salt plus water, salt is a solute, water is a solvent, right. So, this is water is a non volatile, I mean salt is a non volatile component. Water should vaporize, salt will not, right. So, in that particular case, if you have to solve this particular problem, what you need to do? You need to solve the species equation within the liquid, okay. Gas phase already is there, right, that there is this water vapor goes into the air, and then we have taken into account the diffusion terms and all those things. But if you want to do it within the liquid, and this is also important for multi component liquid droplets, okay, the same equation will be kind of valid. So, in that particular case, if you have say for example salt water, there can be other systems also, numerous other systems, we have to, in addition, all the equations are valid, we have to in addition write the conservation of species equation. So, the same equation that we wrote for energy is valid, the same equation that we wrote for the outer phase flow field is valid, okay, except now we have to write the equation for the species inside the droplet. So, here it comes. I hope you recall, this is once again written in the non-dimensional form. Everything else is the same. So, you can just flip your notes and you can see that everything else is absolutely the same. This is chi or whatever you call it, chi or x. Just a notation thing. So, this is very similar to the energy equation, almost identical, right, to the energy equation. Xz that we have written is Xz initial minus Xz at any time instant. This is similar, where we had, instead of Xz we had temperature, in that case, right. So, the boundary conditions, if we have to write the boundary conditions here. So, first the initial conditions when tau is equal to 0, chi z is equal to 0, right, chi z bar is equal to 0 because it is the same as the initial value, right. When neta approaches 1, chi z bar by d theta is equal to 0 because there is no azimuthal variation of concentration on the surface. This is once again the same equivalent definition where we said that the surface temperature is constant, right. Here we say the surface concentration is constant along the surface, but it is varying within the droplet as well as it is varying with time. Okay. So, make no mistake about that. Okay. So, that part, and then the last boundary condition is at n approaches 1, we have 0 to pi chi z by d neta sin theta is equal to m dot into 2 pi r s rho l d 1 2 chi z 0. Okay. So, here in the previous case you had QL, if you recall. Okay. You had QL and you had KL and other things. So, it is the mass equivalent, right. So, that is, these are the 3 boundary conditions or initial condition and boundary condition that is required to solve this equation, right. 1 initial condition and 2 boundary conditions are required, right, because of the nature of the equation, right. So, as you have solved the heat transfer, you can also solve this mass transfer, right. In addition to this, you can solve this mass transfer. So, this is the conservation of species. For 2 species you can write this, right. N number of species you have to write it for the other components also, right, the other species component also, and you have to know the the diffusion of one species into another. So, it becomes a multi component diffusion problem, which is what is similar that happens in the multi component fuel droplet. Say for example, you have a kerosene droplet which has got like God knows dodecane, kerosene, dodecane, N-hexane, N-pentene, all these components inside. So, in order to study that, you have to study the individual volatility of each of the component. So, this m dot that you see over here will be the m dots of the individual components. So, it will be like m dot 1, m dot 2, m dot 3, m dot 4, right, and for each m dot you have to find out what is the corresponding Bm, Bt, etc. Okay. So, that becomes a very onerous task, okay, not within the scope of this particular course, but just to give you an insight that when one of the species is a non-volatile species, you can easily use this equation. It is the same as your energy equation, does not require any other fancy, except that you need to solve this also numerically. That is the only thing that you need to achieve over here, right, and you know what neta is, all those factors we have already defined earlier, tau also we defined earlier. So, this actually tells you that how to attack a problem which is of this kind. So, during the course of this, in summary, what did we do? We have started the problem with the pure we defined what a droplet evaporation is all about. These are all isolated droplets, by the way, and we took baby steps. We first did the d square law, then we slowly cranked up the whole thing, and we showed how the gas phase analysis is done, what is a Faulkner scan type of solution there can be, right. We also solved the liquid phase, we wrote that what equation is valid for the liquid phase. For within the liquid phase, we argued that the Hill spherical vortex is a perfectly legitimate solution, and we identified the different regions in the liquid phase, like which one is the inviscid limit and things like that. And based on all these things, we have provided a global solution for this particular problem, and we have analyzed the data and we have shown what data looks what, we have given correlations involving m dot in terms of Sherwood number and Nusselt number. So, this also, so it has done 2 things. One is that it has provided you with a global perspective, that means what is the evaporation rate, how does the diameter vary. At the same time, it has provided you the insights that, for example, how the flow actually, how the flow profiles and isotherms are, what will be the relative variation of the mass flux. These things which were kind of not very clear earlier on, these are like what we call insights, and these insights have been provided in this particular part of this particular lecture. Okay. So, next thing that we are going to do is that before we go to atomization of droplets, we are going to look into, we have looked into like contact free nice spherical droplets. Let us take a little bit of a look, okay, that what happens when we actually have sessile droplets into the mix. right. That means sessile droplets are droplets which are basically on a platform, right. So, there is a substrate effect that comes into the picture. Remember we did that, we said that there is a CCR mode, CCA mode and all those things. So, these droplets when they actually evaporate, how do they actually evaporate, okay, and what is the nature of their evaporation, okay. So, that is what we are going to do in the next lecture, okay. So, so we end this lecture over here. Thank you.